So, Michael Swafford, yeah, say hi.
Hi, what's up?
So he's chassis, so I guess we'll just kind of go ahead and we'll go from there and just kind of have our discussion.
Okay.
Yeah, so I just got back from California working at NASA 2 days ago. Or yesterday, actually. I'm really screwed up on time. So I put a very seldom amount of work into this since, unfortunately, just being there. But anyways, so this is what the chassis looks like right now. I remember at the last meeting, you said that those front two support structures off of the front hoop need to go all the way to the front bulkhead. So I did that today, and that's all that's been changed. I haven't had time to touch anything else. So that's how it is. And then I think the next slide.
Dave, can you mute your microphone?
Has what we need to do as of what I can think of today. So we still haven't done an FEA on the chassis. So that needs to get done. But we have some more people in the club that have experience with FEA and or ANSYS. So I think we'll be good to start with that. We need to confirm our suspension mounting points, which is with Greg. We just need to make sure that they're in the right place, because he had expressed a little concern about it after running it through, was it K-Factor?
Optimum K.
Optimum K. Yeah, I remember. I don't remember the names of these things. After running it through Optimum K, just to make sure that we're actually optimizing somewhat our design. This is a first-year car, and we know that, but if we can do things right, we'd like to do things right. Then we need to do our SES and then actually make like a design write-up thing for judging. But those are a little bit more future than pressing matters right now.
Okay, can you go back up to a picture of your frame?
Yes.
Okay, so one thing, and maybe this is a question for the project management group, have you requested space envelopes from your other subgroups so that the frame knows how large they need to design around?
Nope, that hasn't been done. It's built way big right now.
Okay.
Like the entire back end is probably 25%, 33% larger than it needs to be. So.
Okay. Have you considered harness mounting bars? In your area?
Those have not been considered yet into the design.
Okay.
Write this down.
How about this? How about you, now that you're back on campus and back from your awesome sounding internship, why don't we schedule a separate chassis meeting and we've got a little more time to put into it?
Yeah.
And then we can talk over some of your frame member choices and FEA if you need guidance or anything on that or space allocation.
Yeah, that sounds really good.
Okay, sweet.
Awesome.
Cool. Alright, so Greg, you want to go ahead with suspension stuff?
Yeah. You want to just hand me that?
Yeah.
Okay. Yeah, I'm Greg, by the way. We met in Lincoln, Mara. I don't know if you remember me or not.
Of course I do.
Alrighty. Well, they can see our screen, right?
Yeah.
Okay. So we've got our suspension, our control arms, and our uprights, our hubs, and everything in CAD. We don't have it perfectly mating with the chassis yet. We need to work on that. But we've got our points and our geometry. We've done some preliminary testing in Optimum K, the suspension software with it. And it seems to work, although it could be optimized a little bit better. So I think that's something we need to work on going forwards. We have an issue with our wheels that we had selected. We're using hubs that we can buy from RCV Performance, and we're having a problem with the brake calipers overhanging and hitting the inside of the wheel, as you can see there. And I've done some research into some other calipers we could use. These ones are pretty thin as far as width goes for what we can find, although I haven't looked at every option. So ideally we need to look at maybe adjusting the wheel, because the company that makes these wheels, Kaiser Racing has like a custom option that they're more than happy to adjust the wheels a little bit for us or work with us on that. They said so. That's something we need to look into, but I'm not exactly sure if there's a better way to fix this issue, being that we would like to use hubs that we're buying online, and which that sets the position for the brake rotor and therefore the brake caliper, so we don't really have a lot of adjustment in that area. So the wheel is really all we can adjust, I guess, unless we get a different brake caliper.
So when you're saying that Kaiser can make adjustments, are they just saying that they have the wheels in many different offsets, so you can choose your offset accordingly?
They have offsets. They can do stuff with the wheel centers and stuff too. They can adjust most of the dimensions, but we just need to work with them a little bit closer on that. I've talked to them about it, and they're willing to do it, but we just haven't gotten to that point yet, I guess.
Okay, so back on your suspension. Do you have engineering requirements? I know you said you're trying to optimize things in Optimum K. What specifically are you trying to optimize for?
Just like the simple stuff like the camber, to make sure it doesn't go positive, and keeping our caster angles not crazy, stuff like that. Basically, just some simple requirements, just to make sure that we're kind of at least in the right direction with things.
Okay, do you have like a chart that outlines your desired value for camber, caster, kingpin,
Yes,
roll center, pitch center?
We do have that. I don't have it up right now, but we do have that we got from MIT. One of the people from MIT kind of sent us some information on it. We got an outline set up for what we want and what we're looking for and what we can do to adjust it for that. So
You got the list from MIT and then modified it based on your overall goals for vehicle dynamics?
yeah, I guess. I mean, we haven't put a ton of thought into it, but we're just looking for a general setup for the car, so it will at least maybe not be working against us, if that makes sense. We don't have or we haven't had a ton of people working on suspension stuff over the summer, so we just haven't had the manpower, I guess, to really have somebody go into the software and do all those calculations and try to get it perfect. But
Okay.
yeah.
So in terms of vehicle dynamics, it sounds like you have a little bit of work to do. Have you thought about design for assembly in your suspension system?
Yes. So I don't have any close-ups of it, but our control arms are going to be made out of 5/8 steel tubing. The plan to make those was to weld nuts onto the end of them and then thread the rod ends into that. The other end of the control arms, which you can't see, are using like the spherical bearings, which will set into the actual control arm, or like a circular metal piece, I guess, a circular housing for them, so they won't just be the threaded rod ends. We need to figure out how we're going to machine, or who's going to machine the uprights for us. They're pretty simple, so they shouldn't need I don't think they'll need like a 5-axis or a crazy CNC machine. They should be able to be machined fairly easily as far as uprights go, I think.
Mm-hmm.
We're going to water jet our brake rotors, because those are custom, and we're going to try to buy everything else.
Okay, couple questions.
Mm-hmm.
So let's start back at the rod end. So on the end, are you using actually weld inserts, or are you just using a common nut to screw your rod ends into the tubing?
A common nut that would be welded on was the first thought we had.
Okay, so they actually make things called weld tube inserts, and they have a longer thread. They're meant to go inside of the tube, and then they give you a small lip to weld around. So they're made for all sizes of tubing, inner and outer diameters. They'll provide extremely more strength because they have a lot more thread length.
Yeah.
So I would suggest looking into those. Are not that expensive.
Definitely.
On that. For the piece of metal at the end where you said you're putting your spherical bearing in,
Mm-hmm.
to a point, are you doing those on a lathe? And is the spherical bearing press fit in, or is it held in snap rings, or how is that method? Okay.
Press fitting is what the original idea was, but haven't done a whole lot of research into that to see which one would be better, I guess, is if we use snap rings or not. But originally we were just going to press fit it and have the machine shop at the college help us out with that.
Okay, so one lesson learned we did a press fit our first year, and we were like, yep, we're going to do it this tolerance, it's going to be awesome, and they fell out when we got into really high loads and hit potholes on the track, so
Okay.
during the testing. So we ended up having to go back in and add a snap ring feature, so just be aware that if you're going to do a press fit, it's very hard to get the tolerance needed to provide enough load to hold those in there during any sort of event where you might hit a bump on the track. So although a snap ring is a little bit more complicated to lay, it might be worth the time in the beginning of your design to add that in.
Yeah, we'll probably just do that then.
Okay. Just wanted to pass that lesson around. Okay, so the next one is, you said you're doing your rotors on the water jet. Are you going to grind that surface of the, do you have any sort of grinding or flattening process? So the rotors that come off the water jet?
I don't know, I guess. The thought would be that hopefully we would do something to get the surface right on them, but haven't looked into that. Basically, we couldn't find rotors that would fit our setup unless we machined our own hubs.
Okay.
So basically where we were at was that we were gonna have to make them ourselves anyways, and I guess hadn't really thought a whole lot about that.
Okay. Yeah, just be cautious of your surface finish, because that's very important during the braking calculations, that you have a really nice fine surface. I mean, most brake rotors are ground to a certain flatness specification.
Mm-hmm.
So just be cautious of that. If you're going to use a water jet, make sure you have a finishing operation on those.
Okay.
Do you guys have a water jet on campus?
Yes. We do.
Would you be running it, or is there someone else who runs it, like in a machine shop?
We have a full machine shop on campus, like on our engineering, or in our engineering building, with like a staff that works full time there, and they would do it for us.
Okay, because so at our school we also had a water jet, but we did not have any clamps, and our machine shop staff didn't believe in using clamps on the water jet, so we held stuff down like giant bricks, and that's not exactly very precise. So I would look into seeing if they have clamps, especially if you need any of these holes to be exact. Most water jets do actually have them, but in the event that you don't, you want to look into that.
Yeah, we'll check that out.
On the top of Missy's point, it looks like you have a floating rotor design in your CAD. So if that's really what you're going to go up with, you want to make the rotor a little bit bigger and then do all your finishing operations on a mill, because the water jet will hold very low, really not precise tolerances versus a mill that can hold 3 or 4 decimal places. So that, to Missy's point, I think make sure you are oversizing on the water jet and bringing it to spec on a mill.
Okay, sounds good.
So last year we made, or not last year, sorry, 2 years ago was the first year we made our rotors in-house, and that's what we did. So we kind of did like the general dimensions on the water jet, so basically the outer circle and maybe like the inner, I don't know, some that weren't like, because you have holes here, I'm guessing, for like just to get rid of mass or for heat dissipation.
Mm-hmm.
So we did some of those, didn't really matter, but then the rest of the holes we cut on the mill.
Yeah, that's a good idea. I didn't think about that.
Neither
Okay.
did we. That's why we're here. So on the upright, has that design been put through any sort of FEA analysis?
Nope. I have that listed on our next thing. We need to get to that and have somebody do that. So
Okay.
we've been pretty short as far as I guess people goes this summer. So
Do we have the knowledge base to have somebody?
we
do
have
that?
somebody that can do it or that in the club that will do it. So
Okay.
yeah.
Off the bat, looking at it, make sure you're filleting any surfaces. You never want to come to a 90-degree bend, especially if force is being put on those 2 little tabs. I'm assuming those are for the tie rods that
Yeah.
go to your ring.
Those are actually filleted in the thing. I don't know why they aren't here. I think maybe I just used an older picture, but yeah, those are filleted in our actual design. So
Cool.
okay, next we had just some parts that we were pretty set on. We've got most of our parts selected. We were going to use some cheaper shocks. I don't know if you guys had any advice on what shocks to use, but we were basically using some shocks for some like midget racing cars that were a lot cheaper than the Olin's ones because we're kind of short on cash.
Yeah.
So I don't know if you had any advice on which shocks to use, but we were just looking for some cheaper ones.
The midget shocks, what spring rates do they come in?
I don't know. Do you know what they came in, Walker?
It's different than like the normal Olin's. But I don't remember what exactly it is. But there's certain springs that you buy for those. That,
Okay.
Walker will look into that, I guess.
Yeah, I guess I have no issue using those midget shocks, especially if it's going to save you money. It's a good reason to pick those. Just ensure that the spring rates that are offered fit in with the designed parameters of your suspension and that you don't have weird, odd frequencies going on just because you picked that shock and it's limited in spring rate. So make sure you're designing to that spring rate, if that makes sense.
Sure, yeah, absolutely. The other thing is that the wheel bearings and the hubs that we want to buy are unfortunately pretty expensive, but we're kind of stuck. We're thinking we're just gonna have to buy them. Of course, we've already designed around them and stuff, but we don't know of any better way to do it because we would like to not machine our own hubs and have to go through that whole process because we're worried that might be more expensive either. Yeah. So my question would be, do you guys know what you spent on hubs and wheel bearings and stuff back when you were doing it? Because it's going to be a couple grand for us, I think. These hubs are super expensive.
So define a couple grand, like $2,000.
Like $2,000, yeah.
$2,000. So, did we send ours out? So our first year we designed them and we sent them out to be manufactured, and part of that was, I will say, quote unquote, donated. So they basically gave us a huge discount because it was a local machining company. But it was probably like $6,000 to $8,000 at the end of the day. So it was very expensive.
Yeah, that's what my worry was. Is unless we get somebody to do it for us, then we're gonna have to just buy these ones and call it good. And we've go ahead.
Oh, I was going to say I have one potential path that maybe your fearless project manager can pursue. Polaris, I do have a contact at Polaris. They do offer wheel assembly kits from like four-wheelers.
Yeah.
New teams for free at no cost if you talk to the right person. So if you're interested, you've already done a lot of design around the RCV, but if you're interested and it potentially saves you money, I can give you the contact at Polaris.
Yeah, we should definitely look into that.
All right, we'll look into it.
Because they do, they would donate the hubs, the wheel bearings, the uprights. It's a pretty cool wheel assembly package. So for a first year team, it might save you a lot of money.
And we'd have our first gold sponsor.
Mm-hmm. And if we were gonna machine our own, all we would do is essentially use a very similar design to the RCV, but just extend this distance between where the rotor mounts and where the wheel mounts a little bit more. So then we'd get a little bit more clearance between the caliper and the wheel, and that would solve that problem for us and maybe save us money on the wheel side of things. So that's all we would do there. But aside from that, we still need to figure out what rockers we're using, our mounting brackets for the control arms. I guess maybe we'll just machine those. We need to find a good master cylinder. We haven't really done anything with the steering system yet. We do have a steering rack that we've found. We need to design a pedal box, and again, we need to figure out our wheels. So I don't know if you guys have any advice on maybe the rockers or steering system stuff for us, but we're really looking for some.
When you say rockers, is that like your
Like the bell cranks for our system?
Yeah, okay. Most teams design those, so you can use simple as designing a triangles, and you almost want to design those so that you can put in the correct motion ratio to your suspension design.
Yeah, that makes sense.
Because everybody's suspension's different, and motion ratio is critical to wheel travel, so you want to make sure you're designing that geometry. And it can be as simple as two triangles cut out on the water jet and slapped together. So
Sure.
I would design the rockers in-house.
Okay, definitely.
You can design rockers.
So for brakes, we did a lot of cars from AP Racing. AP Racing can get expensive. I think that they have a discount for Formula students. You might have to dig around on their website. But just be careful with them because it's not really clear what the specs are of the parts, and we ordered wrong parts a couple times.
Okay. Any other brands that you know of that would work well?
There's a cheap option, and that is to buy a junked motorcycle and take the braking system off of it because a lot of motorcycles are similar in weight to your vehicle's weight.
Yeah.
So that's one option that you can pursue because that would have the master cylinders, the calipers, everything you might need, you know.
Yeah, I like that idea.
So if you could find like a junkyard where the engine is trash but the brakes are still fine. Usually people don't throw out their bike because of the brakes. So you could buy any cheap bike and scrap 2 bikes put together. You might have a nice brake package.
It's a good idea.
It's a damn good idea.
Sometimes I have those.
All right. Yeah, and then we just have some projects left. We got to do the pedal box steering system. We got to do finite element stuff, and we're gonna go back and do some optimum K suspension analysis stuff. And that's, I guess, what we're gonna do going forward. Does that sound like a good plan?
I think you guys are on the right track. I think it would be important to really highlight your engineer requirements and then have a chart to say, yes, I'm on track to meet this, no, I'm not, and how does this impact our overall goals? Because you don't want to design in a silo and you don't want to lose sight of your engineering requirements at the end of the day because that'll hurt your design. So that would be my only advice moving forward, but it seems like you're on the right track.
Actually, going back to Missy, when me and Landon were talking to you yesterday, we figured out something that we'll try out for tracking our progress.
Excellent. Yeah, and I was gonna say what Maura said. So you guys will find this probably in your internships and when you go out to industry. The most important thing is what are you designing to. So you guys are buying a lot of parts, and that's totally fine. You're a first-year team, you have a small budget, it's a lot to tackle. What you really want to understand: why are you making these choices? What does this do for your design? Because they will grill you about this at design, and it could, winning design or doing well in design could really put you guys ahead at competitions.
Okay.
So make sure you really understand why you're using these parts.
Right.
Sounds good.
Cool.
Okay.
Your drivetrain.
Who's doing
Yeah.
drivetrain?
So Jacob, he's our drivetrain lead. He couldn't be here today, so I'll just kind of be filling in for him in the meantime. He was also at an internship and taking summer classes online as well, so not a lot was done. But I still worked with him to at least make our plan concise and know where we're going with it. So we're still keeping our same design idea. We'll keep it simple as possible. We'll just have a chain going from the motor to our differential. And we think that we can probably make the drivetrain fit in around with everything else, with the battery and the other components that'll be in the rear. We think that we should be able to fit it in nicely, especially because it's just kind of like a T shape in general with the shafts and the motor. And then we're still planning on going with an MRX 208. We still haven't shot on the Auburn motor yet. We're trying to look on pricing with motor controllers and other motors, so still trying to work on that, but we are trying to make a decision quickly because we don't know if someone else might bite on that motor. And then for water cooling, and this is actually where I had a question too because I looked into this for a bit. So we found numbers for the Reinhardt controller and the MRAX motor, at least on the liters per minute of how much water needs to flow through. My question was, if we water cool both of them, do we put them in like a series or a parallel tubing scenario? Because I was thinking like, okay, if we have it in series, then it'll probably go to the controller because that'll probably produce more heat, and then you'll have warm water going to the motor, and it's not as efficient. But if it's in parallel, then you're losing a lot of your pressure. So I'm not sure if that's something that you guys did, but what would you guys suggest in that kind of scenario?
I guess my advice would be to map it out and figure out what you're actually gaining parallel versus series. Because
Okay.
you're right on both of your assumptions. One, you'll have a pressure loss, and one, you'll have heated water heading to the next component.
Mm-hmm.
And that might be fine if your system is robust enough to handle a lot of heat in one one line and one coolant tank. But I mean, if you run a parallel system, are you saying that the fluid would come from one tank still?
So parallel meaning like we have one tubing going straight to the from the pump to the
Splitting and then rejoining.
to the motor controller and then back to like a radiator, and then we'd have a separate tube going directly to the motor and then to the radiator and then going both back through the pump.
So would they join right prior to the radiator?
Yeah.
That on one pump.
Yeah.
That's
you just
the
use
that's the
separate-
crux of
well,
it.
You just have separate loops.
Yeah.
Because if you use separate
Yeah, we
loops,
could
you
do
can
that.
just size your radiator to what component you need.
Yeah.
That's like way easier.
One downside is that you'd have to have for the low volt system, you'd have to have an extra pump.
Yeah, but I mean,
But-
like an extra water pumps don't. I mean, it doesn't take anything.
Yeah, it's only
to
like
run
a
water
1 amp
pump.
12 volt thing.
Okay.
Yeah, it doesn't take anything to run a water pump.
Okay. Cool. And then so we do have the MREX motor designed in Creo, but other than that, that's kind of our only part that's in CAD. So right now we're planning on using just regular motorcycle chains and gears because we know that they should be able to hold up to the torque that the motor will produce. And then right now we're planning on getting everything that we have together to know exactly where we are. Then we'll start to pick out our parts, and then once we have the parts picked out, we'll model them in Creo. And then first we'll make an assembly of the drivetrain itself, and then of course we'll mesh it with the chassis to make sure that everything fits together and that it's all working properly.
Okay. On the motorcycle gearing, have you found a motorcycle gearing that is working with your setup for your torque output and your speed output? Or are you just going to take
Yeah.
whatever you think is
See, that's what I was going to ask about is what kind of gear ratio are we going to run? 'Cause if we use a regular motorcycle gear ratio, we're probably going to have way too torquey of a car to drive.
Yeah. So we did do some calculations a while back about a ratio. What did we say? It was like one. It was like a 1 to 1.8 or 1 to 2 point something. But other than that, we haven't looked into exact parts on like for an exact ratio.
You can also get go-kart sprockets.
Yeah.
'Cause, I mean, you can go to a McMaster car and get some pretty inexpensive chains and gears. Sorry. You can find some. You can basically pick whatever ratio you want based on the sprocket sizes on McMaster,
Okay.
and they have matching chain sizes for those sprockets.
That'll work.
Have you asked them about the differential from Kettering?
Then you take it off the motorcycle because the motorcycle's probably overkill in terms of torque output.
Okay.
Huge.
Gotcha.
Can we
Okay.
move the her thing closer to the mic?
1 second. So, and then also, we do kind of have a differential picked out. We've talked with Kettering University. They said they had a used differential. I think it's like a previous version to one of the popular differentials. I forgot the name. But they said that they could probably give that to us for pretty cheap, so we were going to go with that as well.
The problem with their differential is, I don't know if it's a problem, but it's an open differential as compared to like I guess some teams are using a limited slip for the newer ones. We didn't know if that would be a huge issue for us using an open one. We figured since I think it was $400 they were going to sell it to us for, I think maybe we would just go that route and call it good.
Yeah, it'll cause you a little bit of headaches down the road, but if you're apt to have enough people to handle and integrating one of those into your system, then it could be worth the cheap cost.
Awesome.
Okay.
Weld the diff.
Yeah, right. That would be crazy. Okay, cool. That's for the drivetrain. Okay, so then next we have electronics going up here. Pass, you want to come over here and...
Sure.
the slides.
Is it okay if I share my screen? Or
Oh, yeah,
should I
sure.
have
So I'll
access?
stop sharing my screen.
Yeah, 1 second.
And then actually, is Adam going to be with us?
I actually don't know. I talked to him earlier, and he said it was still on for Iowa tonight. I said yeah, so I thought he was going to be here. So.
Should we call him?
Yeah, we have Caitlin with us, so she's our other...
Oh, cool. Hi, Caitlin.
And Caitlin is equivalently smart in the electrical fields.
Good.
So we brought back... Not corrected it to wise. Oh, wise. Right. That means I'm not smart. I'll text Adam, but you guys can go ahead and get started.
Yeah, sure.
And we can join on later.
Sounds good. So
Can you move the phone a little bit
How's it?
closer up here? Merci beaucoup. Okay. Okay, I've got mine up. Actually, if you want to, actually, if I can control it over there just so you guys can see what I'm talking about.
You want this?
Yeah. And where's the, there we go. And actually, I'll just do it from here. Exit. Okay, so I've got this just so the people in here can see, and also, so people, over Hangouts can see. As far as this design review, just going to go through. I've got a few slides. There's quite a bit that we're designing. None of the, it's just a bunch of very small components. And I'm just going to shotgun through them, go over the major kind of design decisions that we've made so far, and just show where we're at. So, same kind of overview that hasn't really changed. I'm not going to spend too much time on that. So as far as the progress that was made over the summer, we've gotten our team organization and project management in place as far as having work routinely done. We've got all of our electronics members trained in Eagle, at least how to use it basically as far as getting a PCB rolled out. We know what has to be done for pretty much every component, or we have the background for the overwhelming majority of them. All the research is done. We've started. Right now, we're basically just at the stage where we're building out prototypes on breadboards, and then we've got a bit of a design strategies. And stage one is just to build something on breadboard with given types of parts, show proof of concept. After you've got something working, transferred over to a perf board, so you've got that design fixed, and then debug it and start drafting schematics and start drafting the PCB in Eagle, and then debug, whittle it down, and then once you've got a final candidate, have it finalized in Eagle for a PCB, and then get that shipped out. As far as we discussed a little bit earlier, we've got the motor and the motor controller fairly nailed down. The battery pack will be the same either which way, and I'll discuss that in just a bit. The biggest detail that hasn't been sorted off is the exact motor controller they'll be used. I'm sure that the actual CAN frames that are used to command the motor controller are going to be different between the two, but they should be roughly one-to-one correspondence, given that the types of things that you're doing are roughly the same, like increased torque, decreased torque, shut the motor off entirely without detaching the AIRs. The other factor that we had to consider was ingress protection. If we go with ours, because we're already going liquid cooled on the motor controller, we'd go liquid cooled for the motor, just to get higher ingress protection for the rain test. However, the one that we're looking at Auburn is the combined cooling, which means it's as good as the air cooled effectively. So IP 6.5 versus 2.1. Anyway, as far as the accumulator, for the high volt battery pack, we're going with what most teams go with, which is lithium manganese nickel, Samsung INR 18650s, 25R. We're going with 80 series 8 parallel, which will give us 288 volts, 3.7 the nominal voltage for each times times 80, which would give us 640 batteries in total. Max continuous draw for max for the acceleration event would be 160 amps, and 46 kilowatt hours before taking the efficiency coefficient into account, and we're going to split that into 4 accumulator segments. One kind of the major detail we still have to nail or to sort out here is whether we want to build our own or go with Intergis packs, given the cost difference. If we save enough money on the Auburn transaction, we'll definitely go with Intergis as far as staying on budget. But the big kind of factor isn't really building it. It's a pretty common do-it-yourself project to build these kind of battery packs. The battery management's a little bit more tailored to electrical vehicles, but there's a lot of counterfeit lithium-ion packs out there, and if we'd be buying them in bulk from Alibaba, which is where we'd see that where we'd realize that savings, where you kind of run into trouble potentially. For the
Hold 1 second.
Yeah.
Be careful with Chinese suppliers.
yeah, they call them shanzai.
They burn everybody, so be careful. And
Yep.
I would say that if you're going to spend your money anywhere, spending them on pre-assembled packs for a first-year team is one of the best, most smart decisions you can make, because a lot of things happen, and they're going to be super critical on you in electrical inspection if you build your own packs.
Right.
So
That
just-
actually, yeah, that's definitely worth that's a factor we didn't consider as far as how the increased scrutiny that we'd see.
Yeah.
Mm.
So then going with the Energus would be a lot simpler, obviously.
Yeah.
Okay.
I do want to
Also-
add though,
oh, yeah.
like, you guys building your own pack would be an awesome learning opportunity for you, and a really good team building opportunity. So even if you do buy your own packs, if you have any type of budget left over to maybe buy some and tinker around, that would be really worthwhile for you guys in the future.
We could actually, so one route to go, and I was going to discuss it later, was we could go that route for the 12-volt low volt pack and, build that out of lithium ion. I was also considering lead acid as far as what is commonly used in motorcycles, sealed lead acid, but I'll get down to that, or I'll get to that in just a bit. But yeah, that is a very good idea. For the accumulator isolation relays, they're just simple high duty or heavy duty single pole, single throw, normally open electromechanical relays. So you drive it with the low voltage pack, and so the low volt pack effectively bootstraps everything. 12, it'll operate a little bit less than that, but we shouldn't have any problem. As far as the current draw, it wasn't too bad either for continuous. There's a peak of 3.8 amps, and then it goes down to 0.3 or something like that for continuous use for keeping the.
Have you guys sourced these yet?
Have we what?
Have you sourced them?
No, we haven't sourced them yet. They, as far as pricing, I saw them at least for DigiKey or Mouser going for $150 a piece.
So there's a company that makes these, and they will give you, I think, two for free if your formula is that.
Which company? We had was it Gigavac?
Yeah, that's a gigavac contactor that you're showing.
Sure, I saw different company names, and I wasn't sure if it was a standardized type versus.
We use them in industry. Yeah.
Yeah. We'll definitely contact them, and I'm not sure if they were listed on Formula SAE's official vendors or official sponsors. Perhaps Hybrid has a list of vendors that pretty much automatically hand out gimmicks to teams. Anyway, the nice thing is we pretty much don't have to worry about any current going through it. However, we do have to worry about the current going through this next part. So when we connect the AIRs, the motor controllers, in order to operate, and I haven't gone through the manuals entirely, but my understanding is that the motor controllers basically charge up to the entire nominal voltage. And so when you connect the AIRs, you have a huge potential inrush that you have to worry about because you're basically hooking up a capacitor, so the transient, you could potentially damage the battery pack due to overcharge, or hopefully the BMS would catch it. But to get around that, when you initially connect the AIRs, you have the path to the motor controller going through a current limiting resistor, and then after you've charged up the capacitors enough to 95% or so, you switch it to a low impedance, basically just a clear connection. However, that means that we've got a timed thing, so this basically just stays on for long enough to charge it up to around 95%, and you just have to pick the resistor and pick the kind of time that you're going for. There's a few programs I've seen, or just really quick, easy calculations on a spreadsheet to come up with what those values need to be. However, the main thing that we have to worry about is that when you go from the resistor to the clear path, the low impedance path, you have to be sourcing all that current through both the AIRs and this part as well for the pre-charge circuit. We didn't see a good way to get around that. But presumably you'd have something that would be rated up to the maximum, 160 amps or 200 amps. I'm not sure if you'd get that in solid state though, or if we'd want to consider electromechanical. Anyway, our next part that we've got is our battery management system. We're just going with an Orion 2. The price was right in terms of what it did. we're just sending out sense wires to each of the. So you have to do it for the number of batteries plus one. So if you've got like one cell, you go the anode and the cathode, and so we're sending out sense wires just to monitor the state of charge, and you can program them in so that it can look at the voltage and then correlate that to a state of charge for each of the batteries, which is nice. And it also it's got a heat sink on it, so it can handle load balancing by discharging batteries that are overcharged, and then when you're charging, sourcing the current to it as needed. It's the communication protocol as far as when it's actually deployed in the vehicle is over CAN, and we'll be using the ECU, which I'll get to in just a bit, to handle that. As far as the temperature sensing, another big project that we're working on right now or that we're currently building out on breadboards, are the all of the lithium-ion batteries. You need temperature sensing on 20% of them. So what we're doing is that at 640 batteries, that's 128 different thermistors that we'd have to send out to it, and so we're using a bunch of multiplexers hooked up just to a single Arduino Mega to you switch through. So like we'll have 16 of these, so we'll read battery 1, 2, 3, 4 up to 16, and then switch to the next series and go down the line and go down the line. And we'll have the Mega communicating any aberrant or any kind of abnormal battery. Yeah.
Hey, really quick. Oh, I was gonna say, have you looked into Orion's thermistor options, because they have
Yes,
their own unit and sensors you can buy from them, and then they all work with the BMS.
Yep, that was a very attractive option, but it was a little bit pricey for what we were looking at. The nicety, and actually the niceness there is actually, we'll want to go with the thermistor option there, because if we buy the Energus packs, the thermistors are included there in the battery, and I think that there's actually one for every two. In the there's a couple different, like they just have a single output or connector pin that you can access those, since those output voltages, and in a fairly it's actually about as plug and play as you can get with the Energus packs. But
Okay, I just wanted to make sure that you knew that was an option.
Yep. The only downside there is that they only do up to like 80 of them, so we'd have to buy like I think 2 of the packs, and they're like $200 a piece, so we'd have to spend an extra $400 on just the thermistor module. What was that?
It does get expensive, because we had to do that also. We had to buy the expansion pack, and then the wire harnesses get expensive. Okay, never mind.
Yep, we're absolutely considering that, and if we go with the Energus, because it's already there right in the pack, that would undoubtedly be the way to go as far as wiring and having everything neat, and it'd be difficult because we'd have to break out every single sense wire on our own if we did something else. So we're aware of the option. As far as that's pretty much everything on the high volt side. We do have some issues, and I'll get to them in just a bit. As far as the biggest concerns that we have right now that we haven't designed for are back EMF and regenerative braking. Just to give a heads up, but that's everything on the high volt side. For our low volt system, it's mostly the 12 volt system in terms of powering everything. We've got a 5 volt system that we might have to come up with a battery for, just to have a stable, ready, 5 volt source, instead of just relying on the transient kind of stuff that you're producing from the buck converter. But anyway, we're considering a motorcycle sealed lead acid battery. We just need to match the amperage is the main thing. This is 1.4, which might be a little bit underpowered. The 5 volt logic stuff all combined is probably only about half an amp, if even that. And then we've got the cooling pump, which is probably going to be the biggest power draw.
Probably an amp.
Probably about an amp.
Yeah.
Which that might be kind of pushing this one right here. So just upgrade it into something nicer, or we can build our own pack there. So that's up for discussion. There are two.
Can you go back to your low voltage battery?
What was that?
Can you go back to the low voltage battery slide?
Yep.
Just be cautious, because a lot of issues teams see is that their low voltage battery will dip under a certain voltage, and then the contactors won't close, and you'll think you have a lot of issues, but really you're just running low voltage. So especially with the Gigavac, you really need to have close to 12 volts, like 11 or 12. Oh, it's in the
Some will do 9. Depends on the coil that you get.
Because as soon as your battery, yeah, so like what Moore's alluding to is like our first year, our car died on endurance, not because of our high voltage pack, but because of our low voltage battery died. So
Oh, for that, yeah, sorry, I forgot to. Yep, for that, we want something that's rechargeable. So actually, lead acid is rechargeable, and we'll have a preliminary. If we go lead acid, the battery management's way easier than what we'll do for lithium ion in terms of how closely you have to monitor it. It's basically just overcharging and over discharge, and there's so many like readily purchasable boards that can handle that. We'll have off of the high voltage pack to make sure that we're not limited off of that in that way. We'll have a 12 volt DC or just a buck converter, a switched power supply to step down to 12 volts to continuously charge. So the main kind of engineering requirement we have for the low voltage pack is to continuously be charged off of the high volt and to discharge as well simultaneously, which shouldn't be too hard to do. For our next component, our major getting into the control side of things now, and that's most of everything that's remaining on this. Our main microcontroller, or our main ECU, is going to be a development board. It's a 5 volt development board from PIC. They have these series where they call them DSCs, which are digital signal controllers. It's a DSP mixed with a microcontroller, and so I assume it just has the instruction set to handle the signal processing if you wanted to do some of that in software, for like if you want to do some of the bandpass stuff on the microcontroller itself as opposed to doing it in hardware. Anyway, the ECU is just going to, when it starts up, is just going to kind of run the program like if you were to, from the get-go until the end as far as coordinating everything else. We also, the next kind of control board we have is the SCU for the shutdown circuit. We're calling it a shutdown control unit because it has to do enough stuff. But as far as what the ECU is doing is it's just checking in user inputs, and mainly as far as the user input that it's concerned with is the apps and the BSE, and translating that into CAN messages that it's going to then spit out. And so we need it to be quick enough to be listening and relaying messages over CAN while also doing that apps or doing the pedal position sensors. And this one was particularly nice in that it's a full. Actually, did somebody join in? Do we have somebody that joined in? I had a.
What?
I don't know, just keep going.
Well, I just wanted to make sure that we still had everybody. Yeah, okay, we still have everybody.
Hey, it's us. We're like losing connection, but we can still hear you, so keep going.
Okay.
Oh, okay.
And we also got the phone going on as
Good backup.
Yeah. 1 second. Just looking for. I'm a TA now. Not knowing the tech. Anyway, so yeah, let me get to the next one. As far as the next design decision, we're going for the pedal position sensors. We're going analog, and that's to be able to read voltage with an analog to digital on the microchip, and not better latency, quicker sampling rates. And one design feature is that we can kind of control the linear response range over the pedal percentage and just shift it up one, so that the only time they will pretty much never agree. The only time that they'll ever hit 5 volts or 0 is if there's a short occurring, and the only time they would ever agree is if there's a short between the two, because the potentiometers will be very closely located on the pedal. So we'll just have two basically goniometers or angular based potentiometers, and using that to translate from the voltage to whatever pedal position travel, and just having them two independent. And then doing something similar for the BSE, but for the apps there has to be a plausibility check between the two. We already discussed the cooling system. And next major kind of microcontroller that we're working with is the shutdown control unit. I'm choosing to go with the same development board just because it has to kind of coordinate fairly well with the ECU in terms of being aware of the overall state of the vehicle and to figure out which instruction sets to go through. But the main purpose of the SEU is just to orchestrate in hardware the shutdown or startup sequences, and to basically direct the pre-charge circuit, the ready to drive sound, the T-cell, and to communicate with the temperature sensing board and all of the various shutdown buttons on the dash and everything. As far as every point, and I don't have very many, but I've got 3 major points that we're still hazy on for some of our systems. So the new FSAE rules state that the TSAL has to, they changed it up, so now it has to, when the vehicle turns on, the 12 volt drives a solid green light, and then when you connect the AIRs after or at any time that the voltage on the high volt rail is greater than 60 volts, it has to blink red. So we're going to handle that with 2 different circuits, one for a red light and then one for a oscillating, one for the green light and one for an oscillating red light. And the thing that we are having some difficulty is in generating the 60 volt reference for a comparator to act on. Our best bet, or that we were thinking, was, so the big issue here is maintaining galvanic isolation between the low volt side and the high volt side. We've got the low volt side powering on the comparator and all the transistor stuff there, and we've got but in order to come up with a reference voltage, we have to have it independent of the high volt side, because it has to, even if the AIRs are disconnected, if there's for whatever reason a high voltage on that high volt line, it still has to be on. It's the whole point is to be a danger detector, basically, like, oh, high volt down the line, don't touch it, even if it's only a transient voltage. Anyway, our idea was to take like an alkaline battery stack, put them up to like 9 volts or 12 volts or something like that, some easy multiple of 3, and then voltage, or then linearly regulate it down to a very precise reference voltage. And we're not drawing much current off this, so it's not too terribly wasteful to do that. And then take the high volt output and voltage divide it down, so that the 2 inputs that you put into the comparator don't have to come the entire way.
Hello?
Yep.
You sounded really far away. I think Adam just joined the call. Adam, are you there?
Oh, hi, Adam. Oh, wait, can you hear us? Yeah. Hi, Adam.
Oh, actually, what do we have from...
You can see me.
Yeah, I'm sharing my screen right now, that's why.
Oh,
Yep. Okay.
Adam, can you hear us? You can? Okay, so something's weird with the audio, so right now we're actually on the phone with Mara.
It's janky as can
Can
be.
we let Adam to the call?
Yeah,
No.
let's see if we can do that real quick.
Oh, like on your phone. Oh, no, you can just let him to the call and hang up. No, that didn't work for us.
Here, I'll try and add him to the call real quick.
Okay.
Ass, how long did you work on this presentation?
Like 3 or 4 hours. It's also to summarize, or just to kind of organize our thoughts so far. The kind of problem that we've been running into is that there's just a lot that we're designing for electronics.
I know, this thing is hardcore.
Yeah.
He's going to answer.
Oh, yeah.
So yeah, it's going through.
Okay.
Which is nice. He's got his microphone muted, and he'll have the audio input over there, and we'll just have a conference call going on.
We've got to try and figure out this audio thing. Hey, Adam, I'm going to put you in with Mara as well.
Yeah. Please enter your password.
Oh, you
Then press pound.
All right, is everyone here?
Please enter your password.
Oh.
Then press
Got
pound.
to be kidding me. Okay.
If you know your party's extension,
Please enter your password. I'm sorry. This number is not valid.
Oh my
Please enter your
god.
password. Then press pound.
Wow, that didn't work.
It's a bad.
Okay. Hold on, guys. We're having some difficulties here.
We should have ordered pizza when we...
I-
You know what I'm saying?
What did I say?
You said you were hungry.
Said I was hungry and we need to go get pizza.
Hello?
Yeah, I couldn't get him on.
Okay, wait, let me try.
Cool.
it's going to be the absolute jankiest thing if you have Mara routing audio for Adam and then us recording this through the mic. But
They got that $5 pizza place now. They don't deliver, do they?
No.
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 They look kind of sketchy, but I've never had them.
What's that at?
Oh, hey, Adam.
It's by the BP gas station across the street from
Adam?
Culver's.
Yes.
There we go.
Cool. Hey, how's it going?
Oh.
Good. Finally.
Good, good.
Someone's echoing. So, Adam needs to mute.
Yeah, if Adam has his audio coming through, it's being recorded in 2 locations, so we'll just want to have it coming through the phone.
Yeah. Looks like he's muted. Yeah,
Oh,
okay,
awesome,
cool.
awesome.
Perfect.
Okay, in
Alright,
that
keep
case,
it up.
I can just do a quick review, just as
Oh, yeah,
lightning
so-
fast as is humanly possible, or maybe not.
Just like
Just what we
skim
have.
over the big things that you talked about. You don't have to go into the
Yeah,
detail
because
again.
I've already been, I don't know, what's, from a professional engineering perspective, Maura, what would you say are the most relevant points I've brought up so far? Because I've just been kind of going through the, or as far as, I don't know to what degree it's mundane or,
What questions do
Yeah,
you
let's
have?
keep going from where we left off. And let's talk about the T-cell a little bit more. I want Adam's
Yeah.
opinion. He knows
Yeah.
the rules better. And
Yeah.
then you can send him his presentation. He can look over the other stuff.
Sounds like a plan. Okay, yeah, so for the TSAL, this is one of our points of contention. So we've got 3 major design points of, or actually 2, just 2 devices that we're, that we have to design that we're pretty shaky on. So for the TSAL, they just updated FSAE rules, and I was going to initially sidestep this by coming up with the laziest possible solution, like as an engineer is wont to do. But they changed the rule setup so that when the vehicle turns on, the default, once the low volt side is on, it has to power on a green safety light, and after a voltage greater than 60 volts, at least referenced from the high volt side to the high volt ground, so it's referenced to the high volt side. Once it's greater than 60 volts, the light has to switch over to flat blinking, 5 hertz or so. And we were kind of curious as to how the best way to generate that 60 volt reference. So, the first thing that came to mind was a comparator. Just have an op amp in there, as a simple comparator, and take the high volt side and compare it to 60 volts as a reference, and use that to activate down the line so by default there's one line, and then you turn something on, and we can generate 2 complementary, when one circuit for the green light is on, the red is off, just by using an inverter and having both hooked up through a MOSFET, so you can control it in solid state transistors like that. But for generating the 60 volt reference, because it has to be, we have to have that reference on even when the EIRs are disconnected, because if the voltage is still high down the line even when the EIRs are disconnected, we need to be able to generate that, and it has to be referenced to the high volt side. So our idea was to maybe take an alkaline battery stack, get it up to like 9 or 12 volts, and then tie that anode to the high volt ground, so that it's 60 volts, or rather 12 volts reference to that, and then take the high volt side as an input and put it through a voltage divider to get it down to that 12 volts for the comparator to act on, and then have the low volt side powering the comparator and powering the lights and everything on that. And I was wondering if that seems like a plausible solution.
It's certainly a plausible solution. It might be a little over-engineered, if anything. If you could just basically run everything through some sort of a FET or relay or something of that nature, do everything at super low voltage. Just divide everything divide the high voltage by 100, and then just do some sort of reference signal that's using a voltage divider, get it so it looks like 0.6 volts, and then anytime those are equal or greater, then you can just have the FET turn on the lights.
Sure, and would we the main we wanted the reference though to be tied to the same ground, so that the 2 references aren't floating between the signal and the the voltage divided high volt side. What's the best way to tie them together to make sure that you're getting that? Do you know what I mean? Otherwise, they'd be floating if you're not tying them directly together. And then if you tie them together with just a signal that you produce like that on the low volt side entirely, then you risk galvanic isolation.
Yeah, but you gotta be careful not to tie your high voltage to the chassis ground, because if you do that, you're going to trigger IMV.
Yep. But what would be a good way to make sure that the reference is that you have those. The problem is in the referencing. So how do you tie together those two references from the high volt to the low volt side, so that you know that when you've got that 0.6 volt signal on the low volt side, that it's 0.6, that they're both the same, because the 0.6 is with respect to the low volt side or wherever you're generating it at. How do you generate it on the high volt side, or a 0.6 on the high volt? That's why we were looking at the battery, was to be able to, because then you can tie the anode of the battery to the high volt side, and you get that isolation there.
Okay, yeah, I see where you're coming from that.
That's the big design challenge that we're running into. As far the battery, just it seems awkward, and actually doing 100 voltage divider means we only have to have a single battery and then just linearly regulate it down to where we need it.
Right.
So it would just be like and the main thing you have to worry about is just making sure that the battery doesn't run out of juice, because then it'll start dipping and it'll start being unpredictable, or you'll start getting weird stuff. But,
Sure. Yeah, let me think on this a little bit longer.
Sure.
But yeah, what you're proposing will absolutely work. Let me see if I can think of a slightly less convoluted way of doing it.
It is really convoluted, but that was I knew for a fact it met all of the design challenges, and but it's really an ugly. It's about as dirty of a solution as you could come up with. Other than paying the mob to do it for you.
Right. Yeah, let me think on it for a minute, and then I will get back to you on other possible options.
Sure, and I'll send you the PowerPoint after this. Up to our next point, we're like 2/3. We're almost through. Our next design thing for a ready-to-drive sound is just going to be fairly straightforward. Just use a 3-watt Class D amplifier, powered off the 12-volt pack, and have the audio signal come off of a wave, an Adafruit board, and go into Logic Pro X and create like a nice little tune for the Iowa fight song or some clip that's like 4 seconds.
No, we can't have that, actually.
No, we can't have school music?
Yeah, no, you have to have like
Copyright.
a distinct, something that's not like a song, like animal noises or something. Yeah, it has to be like a
something like doo-doo-doo. Yeah, or
something like that.
Yeah, okay.
About like the Dukes of Hazzard, the Dixie Horn or whatever on it. That'd be sweet.
As far as our next thing, we're covering safety design choices made for safety devices. For the brake system plausibility device, we haven't designed it yet, and so as far as the engineering requirements, it has to be a standalone circuit board. You have to do everything. So as far as what the goal of the brake system plausibility device is to, when the user requests braking, there shouldn't be any further power going directly to the motor controller. Like braking, in terms of efficiency, you don't have to disconnect the ARs, but you just have to send a CAN message to the motor controller to say, okay, turn off, or they're braking, so don't be torquing the wheels anymore, or don't be, and so this is, something has gone terribly wrong if the BSE signal is active and you're still getting, a lot of power delivered to the motor, and that conditions for half a second. So as far as how we were going to go about it, we were going to, a lot of the stuff in terms of like these digital signals, they get low pass filter just to make sure that transient voltage spikes on the line don't, cause things to freak out. But we're basically just going to have do a little bit of pre-processing on the signal, and then have it spit into an AND gate and say if BSE and power, and so we're going to have a Hall effect sensor on the battery output. There's already one that's included with the BMS, but in order to, I'm not sure if that'll be an easily accessible voltage, for the BSPD. But we just for 5 kilowatts, it's roughly 17.361 amps at that nominal voltage. So we just have to have some kind of signal that once it's above 17.3 or 17 amps, it's considered as an AND. So we just have to reduce it down in Boolean logic to either yes or no for these, and then we just have to have another hard low-level latching type circuitry, or we can either have like a counter that is tied to a specific clock that after it's gone on for so long, then we know it's been 5 seconds or whatever. It just has to be really, really low-level circuitry. It can't be programmable. and then that gets directed to the shutdown control unit, the shutdown circuit, and then causes I think a hard shutdown of the and opens up the ARs after that if it's.
Hey, Michael.
Yep.
Hey, one quick question. Maybe I'm being too much of an MP about this. Can't you just tie in an on-off switch right to your shutdown circuit, so if the brake over travels, it flips the switch and shuts down your system?
That's one of them. That's a different check than what we're looking at right now. So the brake over travel is if.
Different.
What was that?
Oh, they're two different systems?
Yeah. Those are two kinds. So the one you mentioned is a hardware plausibility. This one is more of a, or it's still hardware, but it's. So the one that you mentioned there is if they're pressing the brake, and if to have an emergency like an all else fails. There's tons of. I mean, the vehicle is extremely redundant in terms of the numbers of emergency shutdowns that are on here, but one of them is if they press the brake and it's still not going, they can push it down even further, and that activates the over travel switch, and that's a. I can't remember. I think the over travel switch is actually a soft shutdown. So there's two kinds. Where one is where you turn the motor controller off, or you shut down power while leaving the EIRs connected. The other is you just flat out disconnect the EIRs and you have to go through the discharge circuit and all that stuff. But with this one, it's to make sure that you shouldn't be providing power to the motor when you're trying to brake at the same time. So it's actually a discrete circuit, and it's in order to be a proper safety device, it has to be really low level. So you can't do it. You can't be doing this in programmable logic, and so. Basically, I was just wondering if it sounded kind of coherent. You're basically just trying to, I mean, you have to do some signal processing, but you're trying to basically make a logical and, like, is the BSE on and is power going, is a sufficient amount of current. You have to have a current sensor in order to do it. Maybe just have a shunt resistor or something like that, and just, measure the voltage across it, and then you would know it would be tied directly. But you just have an and. Is the BSE on and is power still going to the motor? If it is, then, and has it been 0.5 seconds, then stop everything now, and it just has to be done on really, really low level hardware. And then
well, is the switch that was mentioned, is that something that would be simpler or could be looked into? Or is that not really gonna be
the brake over travel switch we were just going to buy straight up. It's just a button, and basically the idea is that you've got the pedal coming down, and this is the normal operating range, but if they press it down even further, then something's gone terribly wrong, and that's the over travel switch.
Got it.
And
okay.
that's and the shutdown, the SCU just monitors that all the time.
Got it. Okay.
It's one of the few. It's like one of the multiple emergency stops that like the inertia switch is another one.
Okay.
So, but those are not. They're so easy to use. You just turn them on and just read yes or no for them.
But what he's saying, it sounds like, is that you can't just have that switch. You have to have something else, right?
Yeah, this is an entirely different thing.
Yeah.
Got it. Okay.
It's to make sure that the motor controller and the braking system are coordinating appropriately.
Got it.
And yeah, the other area, we did get our IMD in from vendor. We're just going with the standard IR 155-3203. And as far as how it works, and this is for the benefit of everybody else on the team, just so they have an idea. Basically, you power this thing on, and you power it off of the low volt side, the 12 volt side, and it connects up to the high volt side, and then just spikes high voltage on the high volt side and looks at the amount of leakage current in order to gauge the amount of insulation between the high volt and the low volt side. And there's two outputs that we look at. There's everything is okay. There's an okay signal, and then there's an actual signal that relays the exact resistance calculation. We don't really have to use that one. It might be helpful as far as benchmarking, like how it performs, like in the rain or that kind of thing. But anyway, the main important factor here is that how this affects. This is a hard shutdown or an opening of the ARs if this thing fails, and so that has to be done in low-level hardware. You can't just have a microcontroller read it and then use that to then actuate the shutdown circuit. It has to be low-level enough, so you've got to have this is like a hardware interrupt, effectively. The next, as far as I mentioned, the last slide of the presentation. Thanks for your time. It's been a little bit long, but there's a lot to go over. The biggest areas that we're having right now before we really get everything up and powered is we have no idea how to do proper back EMF protection for the motor controller. The induction motor If you can power it on in order to generate, torque, it works in the opposite way to generate power. So we don't know a good way to channel that effectively. Theoretically, it's tied to the next issue, which is regenerative braking. We'd have a good way. We don't know what all we have to do in there. Our research hasn't been terribly productive on that so far. A lot of the people that design research are like, this is a new way to improve it, or they assume you already know how to do it fairly well. So, yeah.
Is regenerative braking something we should look into or implement?
Or are we likely to fry the motor controller if we don't take it into account?
I would say you have a lot going on right now, and regenerative braking should be very low on that list until you have all your circuitry figured out and it's tested and implemented for a first-year team. Because you showed us a lot of really good components. We haven't seen a lot of circuit diagrams of how that all fits together.
No, we haven't put those together yet. We're, as far as at the stage, after we get the breadboard model up, or after we build something, then we'll know that it works, and we're going to start designing it on Eagle. And but we haven't gotten to that stage yet. We're about maybe a week or two away from getting that kind of work done.
Okay, I would say regenerative braking is low on the to-do list.
Yep. Our main concern is whether if we'll fry the motor controller, because given the cost of the motor controller, it's a potentially ruinous, thing. If it fries and we have to buy another one, we might not have the funds to buy another one at $2,000 to $4,000.
Yeah.
So I think we're just trying to figure out how do we control the back EMF that the motor will give off when the motor's not under power? Is that already done by the controller, or do we have to do something separate?
As long as for anything that's running high current, shielded, grounded cable, ground the shields on your shielded cable, and other than that, you should be fine.
Okay.
That makes sense.
Would that be from parasitic capacitance or inductance on the shielding if you don't ground it? Or just
Yeah.
Okay.
All right.
Cool. That works for that.
You've talked to these guys about the potential motor option, right? And everything.
Yeah, so I know Maura and Missy know about this, but University of Auburn, or Auburn University, I don't remember which one, but they are selling a used motor and motor controller. It's an MRX 228, combined cooling, so liquid and air, and then also a Bamacar D3. And so we did a lot of research at first, okay, can we make this motor work given that it's not waterproof? And then also, given the reliability of the Bamacar, can we make it work? And we think that we can, and we've done a lot of research on it as well. And we asked some other teams as well. The motor doesn't have to be waterproof, it just has to not get wet, so simply covering it would solve that. The Bamacar, we would just have to be very careful with, and we'd probably ask for a lot of help with that from other teams and their use, because when we were going around competition this year, they said it wasn't very reliable. So what we're doing right now is we're trying to look into, okay, before we spend money on this, who might be able to give it to us for free or at a very low or very high discount. So that's kind of what's going on right now with that stuff. But otherwise, yeah, we're still going on hard at sponsorship. Still trying to get a lot of companies together. We start classes officially on Monday, so we've been doing a lot of organizational stuff like that, making sure all of our meetings are together, and making sure that we'll have a good semester and a good year. And yeah, so things have been coming along. I'm pretty proud with everything that's happened over the summer, given how many people were away, and that's actually something that we didn't account for beforehand. So I think we did some good progress.
This has been an awesome review. Thanks everybody for presenting and preparing this stuff. I think you're on a good path. There's still a lot of work to do and a lot of issues to encounter and lessons you'll learn, but it's a good start.
Definitely. Okay, awesome. Well, so thank you guys so much again. We really appreciate this, and we'll definitely stay in contact if we have any more questions.
Awesome. Can you send us your presentation so we can mull over it and then ask follow-up questions if we find anything?
Yeah, definitely. That'd be fantastic. We'll send those over to you right away.
Thanks.
All right.
Okay, awesome. Yeah, thank you so much again, guys.
Thanks, guys.
Thank you.
Have a great night.
Thank you.
Thanks.
Bye.
All right.